Hello, my name is Andrea Reindl and I'm a PhD student at the University of Applied Science, Regensburg. Today I present a comparative analysis for the communication technologies CAN, CAN-FD and Ethernet for networked control systems. I start by giving a short motivation. What are networked control systems? Networked control systems consist of sensors, actuators and controllers, and they have a communication network in the control loop. Several different networked control systems exist, but we further focus on the shown networked control system. This consists of one main controller and several local controllers. The main controller determines the required set points and sends them to the local controllers. The main controller controls the global control loop, while the local controllers control their local control loops. Local controllers can be also added or removed even after a first installation. This increases the flexibility and offers various applications for networked control systems. As the communication network is inside the control loop, it is important that the messages are transmitted fast and reliable, as delays in the communication affect the system control and stability. In the following, we further focus on an example application for networked control systems, the decentralized battery management system. The decentralized battery management system consists of renewable energy producers, variable consumers, and various batteries. All components are equipped with their own microcontroller and respective sensors, and they are connected with a global communication line and a common DC line. One of the batteries is temporarily elected as the main controller and determines the required set points of the remaining batteries. All microcontrollers manage the data relevant for system control, and possible single point of failure are reduced. For the communication in networked control systems, special requirements arise. In order to guarantee system-wide data consistency, it is required to have a broadcast communication. The operating parameters, including, for example, the current value, the voltage value or the state of charge, are transmitted to all the remaining components, and therefore the messages only contain a few data bytes. As the system continuously changes, it is required that these values are sent in periodic send intervals. So we have quite short messages that have to be transmitted in periodic send intervals. As we already saw, these messages contain set points and they are required for the system control. Therefore, the messages have to be transmitted fast and reliable. Erroneous messages should be detected, and error handling or error detection mechanism should be provided by the communication technology. Furthermore, it is required that the communication technology shows a small error rate, as every error affects the system control. The power consumption of the communication technology affects the energy efficiency of the overall system and is, for example, especially important for systems like the battery management system. What kind of communication technologies are considered? CAN is considered. CAN is a well-approved bus communication system. It offers low message overhead, as the message frame is quite short. Furthermore, it offers error detection and error handling mechanism, and the implementation is efficient to be done. On the other hand, CAN communication is limited up to 1 Mbit per second and up to 8 user data bytes per message. So the transmission rate is quite low, and only a few user data bytes can be transmitted per message. CAN-FD, namely Controller Area Network Flexible Data, is the next generation of CAN. It offers increased transmission rates up to 8 Mbit per second and an increased user data length of up to 64 user data bytes per message. Furthermore, it offers improved error detection and error handling mechanism, and the implementation is still efficient. Compared to CAN, the message overhead has slightly increased, and this also means the message overhead is larger, especially for few user data bytes. The transmission rate and the user data length is increased compared to CAN, but it is still limited and it cannot be used, for example, for audio or video data. As a third option, Ethernet is considered. Ethernet offers transmission rates up to high gigabit ranges, but with an increasing transmission rate, also the requirements to the processor and to the memory rise. So for embedded systems, 100-base-T Ethernet is a popular solution. Within the scope of this work, the UDP IP stack was used, and the implementation was realized with the lightweight IP stack. This is only one of several options to realize the Ethernet communication, but it was used within the scope of this work. Next, I describe the test setup. The test setup consists of 2 microcontrollers based on the Cortex-M7 processor and a test PC. All components are connected via CAN-FD bus and via a switch to an Ethernet connection line. For the realization of the Ethernet and CAN or CAN-FD communication, an evaluation board was used that already offered a RJ45 interface and an Ethernet PHY. To realize the CAN-FD communication, an external CAN-FD PHY was added. To measure the transmission time of the messages, a logic analyzer was used. The logic analyzer is connected to the microcontrollers and also via a USB line to the test PC. The test PC manages all tests and the measurement data. So next I show the comparative analysis and the test results. To compare the communication technologies Ethernet, CAN-FD and CAN, the following 5 criteria were established. I start by the message processing time. I shortly give a definition of the message processing time. The message processing time consists of the message generation, the transmission of the message and the unpacking of the message on the receiver side. But it is safe to say that the biggest share of the message processing time is the message transmission. So the start pin of the sender is set before the message is generated, and the stop pin of the logic analyzer is set by the receiver after the message has been unpacked. To determine the message processing time, CAN, CAN-FD and Ethernet were measured using different transmission rates. For CAN, a transmission rate of 500 kilobit per second was used. CAN-FD with a transmission rate of 500 kilobit per second and 1 Mbit per second, and activated bitrate switching with 1 Mbit per second and 4 Mbit per second were used. This activated bitrate switching is signalized by this double-slash operator. And for Ethernet, a transmission rate of 100 Mbit per second was used. The measurement was done for different user data byte length. We first start by a user data byte length of 0 byte. This might seem a bit odd, but this clearly shows the effect of the increased CAN-FD header. So you can see for CAN and CAN-FD with the same transmission rate, it takes approximately 27 microseconds longer to transmit the CAN-FD frame. So if CAN-FD is not required, or the increased transmission rate or the increased user data field is not required, it is still recommended to use the classical CAN. Then next you can already see the effect of the activated bitrate switching. For a transmission of 0 user data bytes, CAN-FD with activated bitrate switching is approximately 20 microseconds faster than CAN-FD without the activated bitrate switching. The reason for that is that this increased transmission rate of 4 Mbit per second is also applied to the CRC field and to the data length field. Ethernet only takes 44.3 microseconds for the transmission of 0 user data bytes, despite of the increased message header compared to CAN and CAN-FD. So for the fastest possible transmission, Ethernet clearly outweighs CAN and CAN-FD. Next, a user data byte length of 8 bytes is investigated. Here again you can see the effect of the slightly increased message header. So CAN-FD again takes approximately 27 microseconds longer than CAN. The effect of the bitrate switching increases with an increasing number of user data bytes. So here the transmission of 8 user data bytes only takes about half of the time compared to the option without activated bitrate switching. The transmission of an Ethernet message with 8 user data bytes takes 44 microseconds, which is faster than the transmission of 0 user data bytes. The reason for that are measurement inaccuracies. Next, 64 user data bytes are investigated. This is the limit of the CAN-FD frame. Here you can see that the effect of the activated bitrate switching further increases. It only takes a third of the time to transmit a message containing 64 user data bytes with activated bitrate switching compared to the option without activated bitrate switching. Ethernet only takes 53.4 microseconds and is significantly the fastest option. If you want to transmit a message as fast as possible, Ethernet is the communication technology of choice. If CAN is sufficient, you should still use CAN because the slightly increased message header of the CAN-FD frame clearly shows an effect. And then CAN-FD closes the gap between the classical CAN and the Ethernet option. Next, the processor workload caused by the different communication technologies is investigated. We saw in the previous slides that the microcontrollers also have additional tasks like recording the operating parameters or calculating system states like the state of charge or the state of health. So it is required that the communication technology only poses a small load to the processor. The processor workload is determined for sending and receiving messages. First, the processor time for the initialization of the different communication technologies is measured, followed by the determination of the processor workload for sending and receiving messages. Here you can see the initialization times for CAN, CAN-FD, and Ethernet. CAN and CAN-FD both require 40 microseconds, as they use the same peripherals. The initialization of the Ethernet communication takes 1.7 seconds. This is compared to CAN and CAN-FD extremely long. The reason for this extremely long initialization time is the Ethernet PHY that was already provided by the evaluation board. If you would replace this Ethernet PHY with an improved Ethernet PHY, then the initialization time would be in the range of some milliseconds. This extremely long initialization time is especially critical regarding possible system restarts. So if one of the microcontrollers is restarted during operation, for the Ethernet communication with this Ethernet PHY, it would take 1.7 seconds for a possible communication. In the next step, the processor times for different send intervals were measured. First, the processor workload for a send interval of 10 milliseconds is investigated. Here you can see that the CAN or CAN-FD communication only takes 0.03% of the entire processor time share. In comparison to that, Ethernet takes 1.8% of the processor time. This is also still quite low and does not pose any significant load to the processor. Next, a periodic send interval of 0.2 milliseconds is investigated. Here, 1.5% of the entire processor time are required for CAN or CAN-FD communication. Ethernet, in comparison, takes 23.6% of the entire processor time. So you can see that the required processor time for Ethernet communication has significantly risen, and it is even possible that the processor workload required for Ethernet communication reaches a critical limit before the minimum send interval limit is reached. So the processor workload depends on the send interval and the communication technology. For Ethernet, the lightweight IP stack was used, and here it has also been mentioned that several threads are used for sending and receiving messages. So the software for the Ethernet implementation is, compared to the one for the CAN and CAN-FD communication, quite complex, which can also be seen regarding the required processor workload. So if it is necessary to have a communication technology that poses only a slightly load to the processor, CAN and CAN-FD communication should be considered. Next, the energy consumption of the communication technologies is determined using the power consumption calculator. The following components are considered. On the one hand, of course, the ARM Cortex-M7 processor, then the CAN-FD interface and the Ethernet interface, the CAN-FD PHY, the Ethernet PHY, and the RJ45 interface. For CAN and CAN-FD communication, the same peripherals are used, and therefore they are summarized to the CAN-FD sequence. Here you can see the power consumptions. The power consumptions were determined in run, idle, and sleep mode. CAN-FD communication and CAN communication requires 375 milliwatt, which is relatively low compared to the power Ethernet requires in run mode. Ethernet requires 705 milliwatt in run mode. This is about 40% more than CAN-FD communication requires. In idle and sleep mode, it can be seen that the sleep mode is advantageous regarding the power consumption. For both for Ethernet and for the CAN or CAN-FD communication, only about half of the power is required in sleep mode. So if Ethernet communication is required due to the increased transmission rate or the increased user data length, then the sleep mode should be considered and applied in every possible case. It can be clearly seen that Ethernet requires much more power compared to CAN and CAN-FD communication. It is about 40% more compared to CAN and CAN-FD. So if it is required that the communication technology only requires low power, then CAN and CAN-FD communication should be considered. In the next step, the error rate is investigated. For this case, the residual error rate is especially significant. The residual error rate describes the undetected erroneous messages compared to the total number of messages. This means these messages contain some errors but are not detected by the error detection mechanism, for example, CAN or CAN-FD already offers. These undetected erroneous messages endanger the system control significantly, and therefore the residual error rate is investigated. There is also an upper limit for the residual error rate. This is an ISO-specified limit, and it says that for safety critical applications, the residual error rate should always be below the value of 10 to the power of -7. To determine the residual error rate, direct code analysis is used. This is mainly based on bit error rate and the CRC. Here different message patterns are applied in order to determine the residual error rate. For the CAN communication, a user data length of 8 bytes is used, while for the Ethernet communication, a user data length of 42 bytes is used. This is of course not the limit for Ethernet communication, but with a rising number of user data bytes, also the effort for this direct code analysis rises. So the maximum for the residual error rate of the CAN communication is 3 times 10 to the power of -15, while for the Ethernet communication it is 7 times 10 to the power of -40. Both communication technologies obtain this upper limit for safety critical applications. So for Ethernet and CAN communication, it is possible to be applied within safety critical applications. The residual error rate for CAN-FD could not be determined yet, as it offers improved error detection mechanism, and the CRC is also improved compared to CAN. Last, the Eric's Fifo load of the different communication technologies was investigated. Therefore, messages containing the maximum possible user data bytes were sent in the shortest possible send interval. And then on the receiver side, it was investigated if an Eric's Fifo load occurs. So the messages are transmitted with the fastest possible transmission rate in the shortest possible transmission intervals, and then the Eric's Fifo of the receiver is investigated. So the messages are sent, and then in the next step they are stored in the Eric's Fifo of the receiver. If a lot of messages are stored in the Eric's Fifo, there is the possibility that an Eric's Fifo occurs. This means that messages are overwritten before they are processed. So here you can see the minimum possible send intervals for CAN, CAN-FD and Ethernet communication, and the measured message processing time for the different communication technologies, and the time it requires to unpack the messages on the receiver side. It can be significantly seen that the message receiving and unpacking time is really quite fast, especially compared to the time it requires to transmit the messages. So in none of the presented scenarios, a significant Eric's Fifo load occurs, and also no Eric's Fifo overflow occurs. So now I draw a short conclusion, especially with focus on network control systems and the example application of the decentralized battery management system. In a first step, we have a look at the required user byte length per message. Within the context of network control systems, only 8 byte or less user data bytes per message are required. A high transmission rate is relevant, as the messages contain data relevant for the system control, and every delay in the message transmission affects the system control and stability. Also, a low processor workload is required, as the microcontrollers have additional tasks like determining states or managing data. And as the example application is a decentralized battery management system, also a key criteria is the energy efficiency. Therefore, for the network control system, CAN-FD communication is the communication technology of choice. Of course, for different criteria, different communication technologies show advantages. Here you can see overview of the different criteria and then the resulting communication technologies. In the next step, CAN-XL is also considered as a possible communication technology for network control systems. CAN-XL is the next generation of CAN-FD. It offers transmission rates up to 10 Mbit per second and a maximum user data length of 2048 bytes per message. Also, energy-efficient Ethernet and time-sensitive networking are considered. Energy-efficient Ethernet has the goal to make Ethernet more energy efficient, and Ethernet time-sensitive networking is an extension of the IEEE to make Ethernet also compatible to real-time systems. And last, Ethernet without stack implementation is considered. And here's a closing comparison. CAN communication is like the bike. If you want to transmit few data with a relatively slow transmission rate, this is the communication technology of choice because it offers high energy efficiency and low costs. For a faster transmission and more user data bytes, CAN-FD is the solution. And if you really want to transmit a lot of user data bytes as fast as possible, Ethernet is the communication technology of choice with the price of high power consumption and also complex implementation. This was a comparative analysis of CAN, CAN-FD and Ethernet for network control systems. Thank you for your attention.